These are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. And I hope you had a good couple of days. I hope you kept yourself busy and did fun stuff and you weren't too overloaded with schoolwork. And I hope you're ready to continue with Arduino. Hey. Oh, hey. So Mr. Dubik will not be joining us today, more than likely. It's possible that he will be, but he's been very busy today, so chances are very good that he won't be able to make it. So I'm going to be taking over the lesson. Unfortunate for you. Ha 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 ha. That kind of fell flat. Anyway, we're going to continue with LEDs on Arduinos, but now we're going to up the ante by sticking more LEDs onto our breadboards, which means more things blinking, which automatically means, it's cooler, right? I mean, that's how I feel. I appreciate it, Sarah. Also, good to see you again. Hope you've been continuing to do stuff with Instructables. And good. Glad to hear it. So yeah, like I said, we're going to start off with a little bit of review though. So if you didn't have the Arduino last time around and you have it now and you're kind of like, I don't really remember what happened, or maybe you do but you said that to yourself anyway, not to worry. We're going to spend a few minutes going over the stuff we went over Monday. My brain didn't want to tell me the proper date. And when I said more LEDs, I wasn't kidding. Connecting 8 of them. So anyway, yeah, the review. First off, we're starting pretty easy. What are these called? Exactly. In fact, if we wanted to get specific, because apparently the slideshow does, these are, oh, the other one says green LEDs. Okay, never mind. This one just says LEDs. What about the longer leg of the LED? What's that good for? What is it? Positive. Yes, it is the positive side. Although I did see somebody say anode, and I like that. However, there is an easy way to remember this. So the cathode is the positive side, right? You get to see my wonderful, wonderful handwriting. No. Okay, you seem pretty sure of that. Now I could be wrong, so let me go ahead and double check that before I start spouting off the wrong information. Because I've been wrong enough times in my life that, you're totally correct. I was thinking, okay, you're right. So the cathode is the negative side. The reason I was getting confused was because I was thinking of cations, which are positive. And the cathode attracts cations. So therefore, the cathode has to be the negative side. So you're totally correct, Brian. Thank you for averting what would have been me saying incorrect things. So yes, you're correct. The cathode is the negative side, and the anode is the positive side. Can't hear anything on your laptop speakers. Maybe your internet? It might work itself out soon. I'm also saying this so you guys understand that I'm not just ignoring everybody. Soon, if not, try restarting our software. Okay, so yes, getting a lot of static on headphones. That Raise your hand if you're getting static, because it might be my microphone. Only a couple of people. I don't know then. Maybe is it hard to understand me? Just annoying. Well, you can maybe try restarting it. It might be your internet connection. Those are usually the two most common culprits when it comes to GoToWebinar. Um, or sorry, the software itself and the internet are the two most common culprits. The most common fix is just to restart GoToWebinar. If that's not the case, though, I apologize. I don't know what else we could do with this case because I know I'm not running anything on my end, so my pipeline is about as wide as it goes for the internet on my end because I've learned my lesson from that. Yes, so cathode is the negative leg, anode is the positive leg. It is the longer leg. So the longer leg connects to the positive, allowing the current to flow through and ultimately allows for the LED to light up. Exactly. It's even here in the diagram. Could I have been more wrong? Yeah, that's just me getting confusing my terms. It'll happen occasionally, but I'll try and catch myself. And I apologize preemptively for those times when I say things that are incorrect. Another simple one. What are these called? Yes, indeed. You can be slightly wrong and way wrong. And yes, these are called resistors. What do they do? Yeah, exactly. Yeah, they limit voltage and current. Now, why would that be necessary? Exactly. Yeah, and that's good point, Sarah. But yeah, um, yes, that is exactly correct. Exactly correct. Sometimes, fire is fun. Sometimes it's not. With your electronics, generally that is not a thing you want most of the time. So yeah, you put resistors into your circuits in order to limit, as it says here, voltage and current, with the ultimate goal of being fire prevention or just burnout prevention. Um, Fires don't really happen all that often. They've happened enough times in my experience, but most of the time, the component you're dealing with will just burn out. An LED will light up until it pops, and then it won't be able to light up anymore. A capacitor might explode, which is bad. It really depends on the different types of the different components. Uh, Regardless, all of these things are generally not desirable. You don't want that to happen. So we use resistors to limit the amount of voltage and current going through, the amount of electricity pressure and electricity speed, I guess, if you wanted to equate that to the water analogy, um, in order to prevent these sorts of things from happening. And of course, one final question: the bands. Why are they colored bands? Exactly. Yeah, precisely. So it's telling us the resistance, the strength of it in ohms, the strength of the resistor, I suppose, how much it can resist. Now, usually the last band, you're going to have like a gold or a silver or maybe no band, and that indicates the manufacturing tolerance. If there's no band, I believe it's plus or minus 15 to 20%. And then with a silver band, it's plus or minus 10, and with a gold band, it's plus or minus 5, which basically means that, like, you have a 220 ohm resistor, right? And you have a gold band on there. Now, because manufacturing is not always a perfect thing, you can't manufacture something exactly the same every time. That's why there are defects and inconsistencies between manufactured components. We try the best we can do, and we get pretty good, but it's not perfect. So having that gold band on there means that that resistor, in reality, even though it's rated at 220 ohms, it can resist. Maybe it's resisting at let's see here, 11. So 209 ohms or 231 ohms, since 5% of 220 is 11. It could be in a range plus or minus 11 ohms from that 220 target, which means you could be getting a slightly more powerful resistor or a slightly less, or a slightly more resistant resistor or a slightly less resistant resistor than what is denoted with the bands, although generally it's not enough of a was the band coloration for 10, like as in 10 and 5 ohms, or 10 and 5% tolerance? Oh yeah, no problem. I'm pulling this from memory, so again, it could be incorrect, but a silver band would denote, a 10% tolerance, and a gold band would denote a 5% tolerance. But yeah, no problem. That's why I ask questions, to make sure I understand what you guys are asking, so I can give you the guys the best answer that I can. Yeah. So now things get a little bit trickier. A little bit, not too bad. But basically now we're looking at how to identify, well, actually it's still pretty easy, how to identify the different pins on the Arduino. How about, or the different components. How about A? What's A going to be? Yep. I said it was going to be a little bit trickier at first, and then I remember they were actually written on the red board. So, okay, B is going to be the analog pins. D is going to be the digital pins. Where's C? Oh, C is right here. C is going to be the actual, CPU on it. 1 is going to be the power connection. I don't know why it's labeled 1 when everything else is a letter, but whatever. Yeah, digital pins, analog pins, power pins. That was actually not too bad. And we'll spend a little bit of time reviewing the code, since I went over that not really quickly, but it was kind of a very high up overview of the code and the syntax and everything like that. I say this says let's review the syntax. This is not something we actually reviewed. These are comments. These denote comments. Basically, the way they work is, oh man, my writing. So if you stick 2 forward slashes in front of something on the Arduino software, you'll notice that it'll turn a different color, usually gray, sometimes orange, sometimes green. It really depends. And B, comments are simply for your own usage. You use them to document your own code, because the computer ignores them. It pretends they're not there. It doesn't see them, for lack of a better term. So you can say, like, this is my code for, this is the LED variable. So that when you declare your LED variable, or whatever, and you come back to it months later. Now, granted, this is pretty straightforward. So if you look at a variable called LED, you go, hey, that's probably holding the pin for the LED, and you don't really need to do much in the way of mental gymnastics in order to figure out what it means. But just in case it was something a little bit more obtuse or arcane or something that was harder to figure out, you can comment it to give yourself helpful notes for later on. Again, um, when you're, if you come back to your code like 2 months later, which is something that's going to happen, or if somebody else reads your code, they're going to be so thankful that you labeled this with a comment so that they know what it means. Because one of the nice things about coding is you can write a particular program 100 different ways, especially as they start to get more complex. You can write them 1,000 different ways, 1,000,000 different ways. You can do whatever you want, and there are a bunch of different building blocks that you can combine them and create new different permutations and how information gets passed from one thing to another. And that's great because that means there are 1,000,000 different ways to solve a problem. However, they're not always easily recognizable at first glance. So you're reading somebody else's code and they're doing something entirely different. You're going, what is going on here? I don't understand why they did this. I don't understand what this entire function does. It seems like it's totally useless. It just passes this here and it does this. Enter commenting. So they can go, okay, I created this method because when you pass a variable from here to here, it doesn't actually contain the information, and then you start dealing with null pointers and everything falls apart. So what I did was just a little simple conversion, and you go, oh, okay, I understand why you did that now. And then you can understand their program and maybe add on to it, or at least dissect it in order to figure out how you can do something on your own, whatever. Now, there are two different types of comments. There's the single forward or the double forward slash, which means a single line comment. That means that if we started typing underneath this, it would no longer be a comment. Anything on this line will be a comment, but only this line. Now, the other type is a forward slash and an asterisk with a corresponding asterisk and forward slash closing it. These are block comments. Now, block comments exist, or basically a block comment can be as long as you'd like. It can be multiple lines. It can be the entire contents of War and Peace. It can be whatever you want it to be, as long as you end it with that asterisk and that forward slash. You can do, ASCII art of the Android droid if you wanted to. Throughout an entire multi-line comment if you were so inclined. And that's fine. The computer's, this is my terrible drawing, the computer's not going to look at it, it's going to ignore it, and so you have nice little art there for you to look at later. But the fact that you're using these block comments means that you can create a much larger, much more comprehensive comment without having to, line comment every single bit beforehand. It saves you the effort, and it allows you to give more comprehensive information before maybe like a large complex part of the code. And here it is explaining it here. So what about these curly brackets? I didn't really go over this when we were doing the coding last time, but now's a good time to go over it too before we get started on coding. What do you think those do? What do you think the purpose of those are? And I'm sure some of you are already familiar with it, but yeah, exactly. It denotes a code block. So when we're doing things like the void setup and the void loop, those two things that need to be in all of our Arduino codes, the two functions, the curly brackets denote the beginning and the end of these functions. So here for the example void loop, this can be 500 lines long, and because we have the curly brackets denoting the beginning and the end, the compiler knows exactly how long void loop is supposed to be. Not all languages are going to use curly brackets for functions. Some, like Python, use indentation. So depending on how your code might be indented, that might denote what is part of a function, what is part of a loop, what is part of a loop embedded inside a function, and all these kinds of things. For some people, that's easier to read than these curly brackets. Some people prefer the curly brackets because the nice thing about the curly brackets is suddenly indentation doesn't really matter from the perspective of your computer being able to read it. You still want to indent things properly because it makes it easier for you to read it. Again, if you come back to it 2 months later, you can go, okay, so yeah, I did this here and did this here, and everything's nice and organized, and I can read it much more easily. But curly brackets, theoretically, allow you to put all of your code on one line. I don't recommend it, but they allow you to. Now we're going to move on to actually creating a variable. Now, when I did the code on Monday, I set up the LED pin without using variables at all, just because it sort of reduced the middleman in viewing what the digital write was supposed to do and the pin status was supposed to do. But ideally, what you'd like to do is you'd like to set it up with a variable. So in the future, if you're working on something and you have maybe like you set up pin 13 to be a test pin or something like that, and when you want it to work, you actually want everything to come out of pin 15. But you're working, you use that pin multiple times throughout your code. Well, if you set it up to a variable, it makes your life a lot easier because you only have to change it once. And the why on that might make more sense as we go along if it doesn't quite make sense to you yet. But it basically allows you to reuse a value multiple times and to change that value much more easily than you would if you were inputting it manually like I did with the code on Monday, where I put 13 in every single time. So what we're going to do is we're going to create a variable called LED pin that stores the integer 12. But we would begin with the int keyword because that would denote that variable as being type integer. Now this means that it can only store whole numbers, which I'm sure you guys are already familiar with the meaning of the word integer if you're not already familiar with programming. So that might be old news to you, but there are different types. There are floating point values, which can hold, decimal numbers. There are character types, which can hold, letters and things like that. There are string types. String is just basically a string of characters, so it's like words that can be printed out to the computer screen, things like that. So since this is a variable of type integer, we start the line with int, and that tells the computer, hey, here comes a variable of type integer. Now we have to do its name, which usually it's good practice to give things helpful names. So in this case, we would go with LED pin. So now anytime we want to refer to that variable, we'd use the LED pin keyword, and we can refer back to it and go like, okay, so we're going to set up pin LED pin to be an output pin, and the computer goes, oh, okay, I guess that's supposed to be a variable, so let me go back and be like, oh, okay, LED pin is a variable of type integer, and it's going to have this value in it, maybe 12. So LED pin in the computer's mind right now is synonymous with the number 12. Or once we finish declaring this, rather, is synonymous with the number 12. So we can use the two interchangeably if we really wanted to. Now, granted, if you're in a situation where you want to use the number 12 for another reason, you would be more than welcome to use the LED pin variable. However, again, we're using this for our own sort of readability sake, and for that reason, using it to be related to LED things might actually make a lot more sense, and it might make it easier for you to figure out what's going on. Anyway, what would go next in this situation? Yep, precisely. So now we've declared our variable. We have to basically set our variable up. We have to initialize it. We have to set it to a value of some sort. We do that with the equal sign. And then a number. And this example is 11, which I don't know why they say, integer 12 up here and then 11 down here. But hey, in this particular example, it's going to be 11. Let's just go ahead and change that to 12 for a future reference. So there we go. Now we've set up a variable, we've given it a name, and we've given it a value. What's the last thing we got to do? Precisely, exactly. We have to put that period at the end of the sentence. Not 112. That's the Arduino doesn't have that many pins. We have to put that semicolon at the end to say that it's the end of a statement. Once we've done that, we now have a fully functional line of code that the computer can parse and understand, and that we could do things with. So in this case, we've created an integer variable. We've given it the name LED pin, and we've set it equal to the value 12. And that's it. Full stop. Done. Boom. That's it for that line of code. We put the semicolon at the end, and that says that it's the end of the sentence. Now we can use that variable wherever. So just as a summary of what we've gone over. And these are actually pretty big parts of code. So, if you run into an error, I'll tell you a lot of intro programming stuff, like when you're first starting to program and things like that, a lot of your errors are going to come from, maybe not putting your code inside of the curly brackets. It may seem like a simple thing, but then, you're just like, oh, I'm just typing, and you put in a new line, and you sort of lose track of your nested semicolons, and you might have a statement that's outside of any function. And depending on the programming language, it might just freak out at you and go, hey, you can't do that. It might say, oh, okay, and then compile the code, and then your code isn't running that particular command, and it's because it's not anywhere where it can actually run it, or maybe it's running it all the time. Who knows? So a lot of not a lot of, but a fair amount of programming mistakes when you're first starting out can be related to the placement of these. There are also going to be a fair amount of syntax and stuff like that until you start getting used to the syntax. Semicolon errors are going to plague you constantly, always and forever. It doesn't matter how familiar you get with programming. It's going to be a long, you're going to have a long session of programming. You're going to spend, hours and hours and hours just banging away at some program. And then it's going to go like, oh, I have an error here. And you're like, what? And so you're going to spend, half an hour searching for the missing semicolon. That's why there's a joke. It's the semicolon is the hide and seek champion of the world, whatever the current year is. That's just always going to happen. And it's just because, it's one of those things where you might get into a groove or something like that, and you think you hit it and you don't, or whatever the case may be. Single line comments and multi-line comments, again, those are useful for commenting. Those are also useful for knocking out like lines of code that you suspect aren't working without deleting them. So you can just comment them. Suddenly they're no longer functioning in the code, but they're still there in case you isolate something else to be the problem. And so you can just get rid of the comment, the double forward slashes in order to bring it back into the code, and everything's hunky-dory again. And yes, I did just use the term hunky-dory. This is how we built the first circuits with the single LED. Now, a lot of that was done on 123D circuit. If you had an Arduino at home, maybe you did it at home as well. Who knows? Regardless, this was how we built the first one. Really simple, as you can see. We just set up pin 13 to be the power. And then we set up the ground rail so that it would, complete the loop and actually provide power to the LED. And once we got everything programmed, the LED would blink. Really super simple stuff. Nothing crazy there at all. And then this was the code from lesson 1. Actually, this is a little bit more complex than the code I was doing. Again, I did not create a variable. I just sort of eliminated the middleman And so these, instead of LED pin, were just the number 13. And my cat is knocking over things in my bedroom. So eventually we'll work our way up to 8 LEDs. For now, though, we're going to get started on 2 LEDs. So I'm going to go ahead and get 123D circuit started up. Show of hands, how many of you managed to snag an Arduino from school so that you could get working on this stuff, and who didn't have it Monday? Cool. Got a fair amount of people. All right, not everybody. That's fine. If you don't worry about it. You can still work on it in a 123D circuit just to sort of get yourself familiar. It's not going to feel like, plugging in physical components, obviously, but it should still give you an idea of what everything's going to look like. Yeah, I hear you, because then you don't have to unplug everything after you're done. That makes perfect sense. Less muss, less fuss. I'm going to rotate my breadboard around and drag it down a little bit. So we're going to need 2 LEDs, 2 330 ohm resistors, and 4 wires. And we're going to use pins 10 and 9 on the breadboard, 9 and 10. So let me go ahead and grab those components right now. Arduino basic kit. Grab an Uno out of here. Somewhere. There we go. Okay. Let's think about it for a moment, as it is wont to do. There we go, Arduino Uno. We'll grab, it doesn't matter what ohm resistor you grab, because we can always change those. Well, we should be able to. Hold the phone. Okay, so we can't actually edit the resistors that are in the Arduino basic kit, which is unfortunate, but we can still grab the LEDs from it. So we'll have 2 LEDs, and all components grid, grab 2 resistors out of this. There we go, perfect. So we'll change these to 330 ohms. Is it 330? Yes, it's 330. Regular ohms, not kilo ohms. And these are the basic components we'll need to get started. Obviously, wires are involved as well, but since we use 123D circuits, they're just click and drag. So this is what our circuit is going to look like. So you can see a little bit of the schematic here. Pin 10, pin 9 on the breadboard are hooking directly up to LEDs, and then they've got resistors on the circuits, their respective circuits, and then they just go into the ground. So let's go ahead and hook this up. So this is that's the positive end. So I'm hooking to my LEDs first, and then I'm just going to have wires run from 10 and 9 to my LEDs. I'll go ahead and change this one to red. I'm going to change this one to orange. So they are similar yet legally distinct from one another. Sorry, lame joke. Now that we've got the okay, perfect. All right, now that we've got the LEDs and the power hooked up, let's go ahead and get our ground placed in here. We'll go ahead and put it onto the negative rail. And we'll change this to a nice black color so we can keep things consistent. Now, granted, it's not exactly good form to have this be an orange wire. It should be a red wire since it's a hot wire, just like this one is. Anytime you have, power coming through that, like from that wire, you want to make it red if it's a hot wire. If it's not, like ground wire, generally ground wires are black in electronics. In home wiring, they can be green, or they can whatever. I mean, home wiring is weird. They don't follow the same conventions that electronics wiring does. So it's not always the best thing to take that as an example. But in electronics, they will generally be black. So now that we've gotten our LEDs hooked up and our power hooked up to our LEDs and our ground hooked up to the ground wire, let's go ahead and stick the resistors on. As you can see, I've got the resistor running from the cathode here over to the same rail, and then it's jumping down to a different one. Nothing crazy here so far. Now we just need to complete our circuit, and we can do that by just drawing from that rail at the end of the resistor to the ground rail. So I know I went over this pretty quickly. Show of hands if you got it done. If you want me to go over anything again, don't worry about it. Feel free to tell me. I'll be happy to tell you what everything hooks up to. But otherwise, it should be pretty similar to the single LED. It's just now you've got a second LED setup. Give everybody a minute or two to get that sort of hooked up. Once I see the bulk of the hands are up, I'll then move on to the coding aspect. And that goes in general too. I know I tend to talk pretty quickly. If you guys want me to slow down on anything or go over anything again, don't be afraid to tell me. I'd be more than happy to. I just tend to throw a lot of information all at once. So my speaking speeds up in order to fit all of that useless information in there. The tangential information, I should say. It's not like you guys are learning useless things. Otherwise, where would I be in life? I mean, man. Let's wait for a couple more hands and then we'll move on to the coding aspect. Keep the screen paused while I queue up the next part too. All right, cool. So now that we've gotten that bit done, let's go ahead and move on to programming two LEDs. So again, just to review a little bit from lesson 1, we defined the digital pin variable. Well, we didn't, but in lesson 1, this is the thing that happened. Put everybody's hands down. And then it was used throughout the program. So it was initialized as an output, and then it was switched on and switched off after a delay. So we're going to do a similar thing here, except we're going to use two variables. So let me go ahead and get Arduino open again. Bing, bang, boom. I say that, it's still loading. Boom, okay. So let's go ahead and start off with our void setup and our void loop. since we know that those need to be a part of every Arduino program, always and forever. Quote Napoleon Dynamite here. Now, you remember that thing I said about how most code, pretty much all code, is going to go inside curly brackets? Well, as with all things in life, there is an exception to that rule. In fact, there can be multiple exceptions to that rule. Today we're going to go over one. Where do I go to type code? I downloaded or do you mean on 123D circuits or on my computer? Well, okay, so if it was on 123D circuits, if you click on the Arduino, well, you don't even have to click on the Arduino. You can bring up the code editor with the button near the top. And that brings up it. Oh, it doesn't have to be plugged into the computer yet, no. You can if you want to right now, but it certainly does not have to be plugged into the computer yet. The only time you have to plug it into the computer is right before you're ready to upload the code, because then the code, it needs to be plugged in so the code can be uploaded. Or if you want to provide it power and you don't have the AC adapter for it. But right now it does not need to be plugged into the computer. No, you can run the Arduino program without it being plugged into the computer. Just make sure it's okay. Because mine is not plugged into the computer right now. Yes, so that one exception to the on, of course. Okay, there we go. I need to restart my Arduino program because it's doing that thing again. That lovely thing it loves to do. Okay, so void setup, void loop. So like I was saying, there are some exceptions to the rule. This is one of them. We're going to put our variables outside of any of these functions. Now, does anybody know why we might do that? Just maybe from previous programming experience or anything like that. Heh, I like the terminology. Nice, exactly. Yes, precisely. So, in order to save up on memory, allow us as programmers to reuse variables, and to sort of simplify the whole information storage and exchanging process in programs, for things like variables, there exists a property called scope. And all scope means is where the program can see that variable in the simplest terms. So if a variable has a scope of setup, setup can use that variable whenever it pleases, but only setup can. Loop cannot see it. Any other functions we create will not be able to see that variable because its scope is only within setup. Once we leave setup, that variable, because its scope is only within setup, is destroyed. I mean, it's a bit of a dramatic way to put it, but the computer stops keeping track of it. It goes, you don't matter anymore, leaves it alone. Now there are, again, exceptions to that. If we call up another function, and we use it's embedded within setup, and when we go back to setup, it will remember that variable again. It's not like it's lost forever, but if it knows that it's not going to come back to setup, as soon as it's done with it, it just forgets that variable. It goes, I don't care about that anymore. So variables can have what's called global scope. And that means they exist and are visible across the entire program, from beginning to end. All of the methods or functions can see it, can mess around with it, can whatever, can interact with it on some form or another. For smaller programs, variables with global scope are totally okay. They're fine. You can do that as long as, you can have a bazillion variables if you wanted to. It's not exactly a good programmer, practice, but you could if you wanted to. You could have a bazillion variables, and they could all be global scope, and your setup and loop could interact with them as much as you'd like. As your programs get larger, though, it becomes more dangerous to have global scope variables, because then you forget where other parts of the program are messing around with them. You might have them do unexpected things, and suddenly your program gets wonky and it gets really difficult to tell what's going on. So global scope variables are kind of like salt. They should really be used sparingly, or better than salt. Let's say hot sauce. They spice things up, but you shouldn't use them all the time. In fact, for the sake of your stomach, sometimes you want to use them as sparingly as possible, because otherwise unexpected things happen. That turned a little weirder than I meant it to, but whatever. Anyway, so what we're going to do is we're going to declare two global scope variables here. We're going to call them LED pin 1 and LED pin 2. Now, because we can call variables whatever we want, LED pin 1 and LED pin 2 are not pin 1 and pin 2. They're actually pin 9, and pin 10. However, these are the first and second LED pins that we're going to be using. So that's why they're given the names LED pin 1 and LED pin 2. Sometimes understanding the distinction between the nomenclature, the name of the variable, and what it stores can be a little bit weird and wonky. But as it stands right now, just know, we could call these, if we really wanted to, we could call these Bob and Tim. If we wanted to. These would be unhelpful names, so I wouldn't recommend it. But we could call these Bob and Tim, and then we could use Bob and Tim throughout, and the same thing would be accomplished. But we're calling them LED pin 1 and LED pin 2, so we can keep track of them more easily with a helpful name. So now in setup, just like we did before, we're going to set up our LED pins to be output pins. And this is so they will send electricity out. And so the Arduino knows that, because we don't want them to be taking in electricity. Nothing's really going to happen. It's not like bad things are going to happen. It's just nothing's really going to happen. So now we've got LED pin 1 and LED pin 2 both set to be outputs, which, as you guys know at this point, LED pin 1 is pin 9 and LED pin 2 is pin 10. Boom. So that's what we've done so far. In a few more lines of code, but what we've done is we set up the framework to make the rest of it easier. So we've set pins 9 and pins 9 and 10 to be output. Just like what happened here. You see, I never steer you wrong. Now, we're going to digital write them. LED pin 1, high. Remember, it has to be all caps. You can't just capitalize the first letter of the word like I just did. and also you can't type digital wire. It's really hard to talk and type at the same time sometimes. So, yeah. So you'll notice we've got 2 digital writes now. We're all going to have 1 delay though, because the delay is an Arduino-based thing. We don't have to delay these individual wires. All we're doing is we're delaying the count on the Arduino. If we put delay in twice, well, we would, if we did 2 delay 1000s, we would double the amount of delay time, which would make it 2 seconds instead of 1. So in this case, even though we're doubling the amount of digital writes, we don't have to double the amount of delay unless we, wanted to, unless we wanted to have it be 2 seconds in between. And we'll write them to low and put in 1 final delay, and that will actually be the code for 2 LEDs, which is really, when you get right down to it, pretty much the same thing as 1 LED. Nothing crazy here. So what I'm going to do is I'm going to go ahead and I'm going to put it into my 123D circuit so you guys can see the result of it. And I'm going to hit the upload and run. And boom, there you go. The lights both blink on at the same time and blink off at the same time. Now, for those of you at home, go over the process of plugging it in one more time. Remember the trick with the serial ports. As you can see, serial port COM1 is the only one visible right now until I plug in my Arduino. And give it a second to figure its stuff out. And look at that, COM1 and COM4 are now both visible. COM4 is checked because that's the new one and because it's the same one from last time. And cool. So let me go ahead and try uploading it now. And I can't because this whole thing is freaking out at me. Apparently it really doesn't like me to record the screen, transmit the screen, and use something that apparently uses a 3D renderer to update at the same time. No, it doesn't use a 3D renderer. But it might use the graphics card for it. That's just me musing. That has nothing to do with anything that you guys need to know. Well, okay, so it's not cooperating with me right now. Verify, compile. Just go ahead and do that and see what happens. Okay, so now it's 7:54, so I'm going to leave you guys with a really kind of, it's a nice little introductory quiz. So if we wanted to make it so that the blinking on these LEDs alternated, how would we do that? Yeah, I have a delay down here and a delay. It might not be showing up right now, but I've got 2 delays right now. Oh, you wanted to put them in between each digital, right? Ah, okay. Yeah, you could totally do that too. And yeah. All right. So yeah, that's totally. We got a couple of different ways we can do this. So let's go ahead and let's try it this way first, because that actually seems kind of interesting. Of course, if it wanted to. Oh, I have to. Yeah. So we've got the first solution is just to switch to the highs and lows. So if we were to upload and run that, there they go, switching off. Another solution is we can actually move this delay and move another delay right here. Repeat forever command. Well, it automatically already repeats because it's inside a void loop. So that's the nice thing. As long as the Arduino has power, it will always repeat what's in the in void loop. Yeah. So this is another way to do it. If we put a digital write in between the delay, or sorry, a delay in between the digital writes instead of in between the blocks of them. That switches them off too. So there are, like I said, the same question, already two different solutions to it. Thank you, Sarah and Brian for those suggestions. And for, let's see here, for everybody here, does anybody have any questions about what we've gone over so far today? Well, what we've gone over today. Okay, yeah, seems like you've got a pretty good handle on what's going on. All right, if you don't have any questions, yeah, you're more than welcome to cruise on out of here. I know you got stuff you got to do. Have a great weekend, and we will see you on Monday. And see you later. No problem. PowerPoints or records of those sessions, or is all of this? Well, let me go ahead and double check the handout we've got right now. Slowly. Oh yeah, this is webinar 1. Okay, perfect. Yeah, everything that we went over for the first couple of days is going to be on this handout right here. Otherwise, you haven't really missed much of anything, because we did pretty much the same thing for the first Arduino project. It was just we did one LED instead of two. And then we spent some time going over 1, 2, 3D circuit and stuff like that. There should have been lessons up on YouTube. This one will go up on YouTube. Unfortunately, I'm not sure what the deal is with the earlier ones, but all of the information that we've gone over is in that webinar 1. It's the same exact thing. Yeah, let me see if I can't choose this file. Give me a moment. If it can, yeah, because if I can put it into the handouts, then that'll just make things easier for everybody. Getting that downloaded right now. Cat just walked over into the living room and laid down and cleaned himself after knocking over stuff in my bedroom like he's so proud of himself. Good job, cat. Good job. Okay, I am uploading the second PDF right now, and it's actually lessons 2 and 3. With Vex Robotics, no, I can't say I have. I'm familiar with them to a certain degree, but I've never actually had much firsthand experience with them. Is that what you guys are going to be using in addition to the Arduino stuff, or is that more just for your own use? Because I'm going to be honest with you, I'm not entirely on the up and up of like the competition that you guys do. As I understand it, there's going to be some troubleshooting and things like that, but I don't know like what materials you guys are going to be using and stuff like that. Oh, you used it in your engineering class. Okay. Let me look it up real quick. Vex Robotics. Oh, yes, yes, yes. Yes, okay, this is coming back to me now. When we did a robotics competition early on in my college days, we briefly debated using Vex, and then we decided to go with our own materials, and we used an Arduino Mega, I believe, a couple of Arduino Megas. Curious about this programming software, though. Did you have any questions about it, or just wanted to get my opinion on how I felt about it, or? Oh, this looks a lot like Java or C. Robot C. Huh. Okay, well that explains a lot. Gotcha. Yeah. No, I'm a big fan of the C programming of languages, as you'll probably hear me, wax poetic about a few more times before you're done with me in programming. Um, I like the amount of flexibility you have with C. It's not as oh yeah, this is definitely C. It's not as like Java can be nice because Java does things like garbage collection. It does things like automatic, pointer creation and destruction and stuff like that. Which is, if you don't know about it now, you'll definitely get familiar with it as you get further into programming. And it can be nice for that kind of stuff. It can be useful for sort of automating some of the more finicky parts of programming, um, which is, I imagine, something you're never going to run into like when you're doing Vex robotics and stuff like that. But you might. I don't know. Anyway, however, that it's for those reasons actually that I prefer things like C and stuff like that. I prefer having more control over um, when I'm going to create and destroy things in the memory of my own computer because I suppose, a megalomaniac like that. But it's like the difference between an automatic and a manual car that used to be made. Um, a manual car is certainly easier to drive, and it looks like lesson 2 and 3 just uploaded right now. Perfect. Yep. So, um, oh, looks like Daniel already left. Darn it. Okay. Anyway, automatics are easier to drive. However, it was the case for a long time, it's becoming less and less true nowadays, but it was the case for a long time that automatics didn't really excel at any particular thing. Like you could drive with more. If you drove a manual car, you could drive it so that it was more fuel efficient than an automatic car, based on the way and how often you shifted the gears. If you were so inclined, you could drive a manual car so that it was better at accelerating than an automatic car was. Again, based on the way that you shifted the gears and drove it. So it's kind of a similar idea with memory management in Java versus C. It's a lot easier to have something automatically do memory management for you, but I like the control that C affords as far as memory is concerned. And that was me just getting on a huge tangent, which is, to be honest, probably not terribly related. But, a lot of people think that C is a scary language or C is difficult to understand or whatever. It's not. It's really not. If I started teaching it to myself when I was 9, you guys have got this on lock. It's it's really not as scary as people make it out to be. Yeah, exactly. I really enjoy it too. It's very, very powerful when it's kind of like you get the ability to mess around with the inner workings of the computer through code, um, much more so than you would with a lot of other programming languages. And it's very lightweight and it's very powerful for those reasons. There are more lightweight languages, but none that are as fun to use as C are. But yeah, that's my opinion on that. I'm glad you like C too. It's a good language to learn. You can do a lot of stuff with C actually. You can do um, a lot of really serious programming with C because it's used in stuff like avionics, um, and forms of it are used in automobile programming, things like that. Like the computer that regulates uh, fuel mixture and when to shift and when to turn on ABS and four-wheel drive and all that kind of stuff in cars. That can be used. Like a lot of times, a variant of C is used in that as well. But yeah, anything else you're curious about or had any questions about? All right, well, I'm gonna drop off here and start getting some of my work done. Um, so I'll leave you guys with this. Have a great weekend. Do some fun stuff, whatever that might be, and we'll see you guys on Monday, probably with Mr. Dubik again. Yeah, no problem. Have a good one, you guys.